Welcome to solverfy.
42.52, we're told that sometimes a nucleus can decay by emitting something that's more massive than an alpha particle, presumably if the new nuclide or the other nuclide is also fairly stable. So we're asked to consider the decays of radium-223 first into lead-209 and carbon-14, and then into radon-219 and helium-4. So this is an alpha decay, and this is a carbon-14 decay, I guess you'd call it. So we want to calculate the disintegration energies for this, and then we're told that the Coulomb barrier height for the alpha particle emission has a certain value of 30 mega electron volts, and we want to find the barrier height for the carbon-14 emission. And there's a table of atomic masses that go along with the problem, or you could look them up somewhere in order to actually get to the numerical answers we're after. So the disintegration energy for the first one here is the mass of our radium minus the mass of our lead and carbon times c squared. And so this is 31.8 mega electron volts. So it turns out this is actually energetically possible because it will release energy when it happens. So this can happen spontaneously. Now for our second one, again we have the mass of our radium atom now minus the mass of our radon and helium times c squared. We find that this is 5.98 mega electron volts. So this also releases energy, although not as much as the carbon-14 decay, or the decay involving the carbon-14. We're not considering the fact that carbon-14 itself decays, which is used for radiocarbon dating. So we know that the potential energy is, proportional to the charges divided by the distance between them. And so what we can do here, this is 2, so this one is 1. We want to find the barrier for the first one here. So the second one involving the alpha particle is 30 mega electron volts. And what we can do is just take the ratio of the two things that are the expressions for this, then multiply by this, write it down. We know that U1 divided by U2 is going to equal the charge of the lead nucleus times the charge of the carbon nucleus divided by the charge of the radon times the charge of the helium. These are the charges of the nuclei, because the R's will cancel then. And so then just multiplying both sides by U2, we get this expression. the charge for lead, that's a charge for carbon, and of course the radius of the uranium nucleus doesn't change between the two because, I'm sorry, not uranium, radium. Radon, helium, and so then the barrier for this is 86 mega electron volts.